Hi guys, so today I'm going to tackle with you the University Physics with Modern Physics Volume 1, 14th edition, and this book was written by Hugh D and Roger A. Freedman. So we're going to tackle 3 problems from this book, and we're going to answer exercises and practice problems. So referring to the book, we're going to answer Chapter 9, which has a title of Rotation of Rigid Bodies. So, I'm going to present you 3 problems and I'm going to go through them step by step so that you will get how to compute for the upcoming problems ahead. So for problem 1A, what angle in radians is subtended by an arc 1.57 meters long on the circumference of a circle of radius 2.45 meters? What is this angle in degrees? So it's stated in the problem that it has an arc length of 1.57 meters long. So we have to list that down. S stands for arc length. So, and it's also stated in the problem that the circle has a radius of 2.45 meters. So, we have to write it down. R stands for radius. So, remember the formula for degrees in a circle that in physics that you have theta is equals to arc length over radius. So, using this formula, S, which is 1.57 meters, divided by R, which is 2.45 meters. This equates to 0.641 radians. And the problem is asking, what is this angle in degrees? So we still have to convert this into an angle or into angular units. So we know that one radian is equals to 180 over pi degrees, or we will use 180 over pi to convert 0.641 radians. And using this, we will get 36.8 degrees. So that's how you get the angle or theta using this formula. Okay, so next problem. Problem 1b. An arc 13.3 centimeters long on the circumference of a circle subtends an angle of 125 degrees. What is the radius of the circle? So, again, the arc length is given, so we'll list that down. S is equals to 13.3 centimeters. And the circle subtends an angle of 125 degrees. So, the angle is given, but it is in degree units. So, we have to convert it to radians. So, to convert it to radians, we use the previous formula, but we multiply it by its reciprocal, which is 125 times pi over 180 degrees. Notice that in the previous problem, we multiplied the radians to 180, then divided it by pi to get its degree units. But in this problem, since the degrees is given, we have to convert it to radians first. So we multiply it by pi over 180 degrees, which we get its radian units. So which is 2.18 radians. So using the previous formula again, with a little bit of algebra, we isolate R, which would result to radius is equals to arc length divided by theta. So using this formula, we plug in the values. So arc length, 13.3 centimeters divided by the degrees or the theta, which is 2.18 radians. This would equate to 6.096 centimeters. So the radius of the circle is 6.096 centimeters. Okay, next problem. Problem 1c. The angle between two radii of a circle with radius 1.60 meters is 0.800 radians. What length of arc is intercepted on the circumference of the circle by the two radii? So, The radius of the circle is given, so we list that down. R is equals to 1.60 meters. And the theta is also given, which is 0.800 radians. So we know we don't need to convert the theta anymore because it's already given. So using a bit of algebra again, using the previous formula that we used on 1a and 1b, we isolate the arc length, which is s, because the problem is asking for the arc length. So we get arc length, or s, is equals to radius times theta. So using this formula, we plug in the values. So the radius is 1.60 meters multiplied by theta, which is 0.800 radians. So we would get 1.05 meters. So this is the arc length of the circle. Okay, so next, we're done with problem 1. So we will proceed to problem 2. So problem 2, a bicycle wheel has an initial angular velocity of 1.35 radians per second. So for letter A, if its angular acceleration is constant and equal to 0.310 radians per second squared, what is its angular velocity at time is equals to 2.65 seconds. The problem stated that the bicycle wheel has an angular velocity of 1.35 radians per second. So, an angular velocity, the symbol for angular velocity is omega. So, since it's initial, it's omega sub I equals 1.35 radians per second. So, this is your angular velocity, your initial angular velocity. So, we list it down, and then the angular acceleration is constant and is equals to 0.310 radians per second squared. So, angular acceleration, the symbol for angular acceleration is alpha. So, we list that down. No need to convert because it's in the right format or in the right units. And it's asking the angular velocity at t is equals to 2.65 seconds. So, 2.65 seconds has passed after the bike has accelerated. So, using one formulas of the four formulas when computing for constant angular acceleration, we will use this formula, which is final angular velocity is equals to initial angular velocity plus angular acceleration times time. So why did we use this out of the four formulas? Because the formula has the formula is most suited for the problem because the initial angular velocity is given and the angular acceleration is given and the time is also given, so it matches the formula on the right side. And then the problem is asking for the final angular velocity because after 2.65 seconds has passed. So we use this formula out of the four because it's the most suited formula for the problem. So using this formula, we plug in the values. Initial angular velocity plus, which is initial angular velocity, which is 1.35 radians per second, plus angular acceleration, which is 0.310 radians per second squared, multiplied by the time, which is 2.65 seconds. So computing this, we would get 2.17 radians per second. So this is the final angular velocity at t is equals to 2.65 seconds. So let's proceed to problem 2b. So through what angle has the wheel turned between t is equals to 0 seconds and t is equals to 2.65 seconds? So the problem is asking for the change in angle. So we can't use the previous formula because it doesn't have the theta or the angle in the formula. So out of the 4, we would use this formula to solve for the change in angle. So change in angle is equals to initial angular velocity times time plus 1/2 of angular acceleration times change in time squared. So let's list the given. We will use the initial angular velocity on the previous problem stated on 2a, and then since the angular acceleration is constant, let's also list that down. And we have 2 time intervals, which is initial time is 0 seconds and final time is 2.65 seconds. So let's plug in these values to the formula. So 1.35 radians per second multiplied by the change in time, which is final minus initial time, which is 2.65 seconds minus 0 seconds, plus 1/2 of angular acceleration, which is 0.310 radians per second squared, multiplied by the change in time squared, which is again 2.65 seconds, minus the initial time, which is 0 seconds, and you have to square this. So solving this or calculating this, you would get that the change in angle is 4.67 radians. So since the problem doesn't state that you need to change it into degree form, this would be your final answer. But if you want to convert it to its degree form, you can again use the previous concept that we learned so far, which is you would multiply this by 180 and divide it by pi. So you would get its degree form. Okay, so we're done with problem 2. So we will proceed to problem number 3. So for problem number 3, in a charming 19th century hotel, an old-style elevator is connected to a counterweight by a cable that passes over a rotating disc 3.00 meter in diameter. The elevator is raised and lowered by turning the disc, and the cable does not slip on the rim of the disc, but turns with it. So this is the figure. This is the disc, and this is the counterweight, and this is the elevator. So it's a primitive style elevator. So it's like an old model of elevator which doesn't have electronic capabilities, only purely mechanical, purely forces, purely tension. So the cable that goes through this disc does not slip. So we know that this arc length is equal to the length of the string or the cable wire that goes through this disc. So this is the counterweight and the elevator. So we also have 3 items for problem number 3, namely A, B, and C. So for letter A, let's head first for letter A. So at how many RPM must the disc turn to raise the elevator? At 20 centimeters per second. So it's asking for the radius per minute. So since we're given that the diameter of the disc is 3.00 meters, so we list that down, and since we only use the radius of the circle, we divide that by 2, which we would get 1.50 meters. And also for this item, or from item A, we're given the velocity of the disc, or the velocity of the turning of the disc to raise the elevator. So since the values or the units of the velocity is in centimeters, we have to convert that to meters. So using this, we would divide 20 centimeters per second divided by 100, so that we would get its meter form, which is 0.20 meters per second. You can also convert the radius into centimeter, but or vice versa. You can, so that they would be in the same units, but I would prefer meters because it's most commonly used in physics, or it's the most commonly used units when solving for problems in physics. So I converted centimeters into meters instead of the other way around for the radius. So we have another formula for the angular velocity, which is velocity over radius, or velocity divided by radius. So we will use this formula because we will use this formula since the velocity and the radius is already given. All we need to do is plug in the values to this formula for the angular velocity. So we would plug in the velocity 0.20 meters per second divided by 1.50 meters, which we would get 0.13 radians per second. So, but the problem is asking for the asking for RPM units. So we're not done yet with this. So we still have to convert this into RPM. So we know that 1 RPM is equals to 0.1047 radians per second. So using this knowledge, we can convert radians into RPM. So we only have to divide 0.13 radians per second divided by 0.1047 radians per second. And then we would get its RPM units, which is 1.24 RPM. Okay, so next, problem 3B. To start the elevator moving, it must be accelerated at 1/8 times gravity. What must be the angular acceleration of the disk in radians per second squared? So we're given the acceleration, which is 1/8 times g. G stands for the acceleration of gravity. So we know that the acceleration of gravity is 9.8 meters per second squared. So we have to solve for this, and inputting this in your calculator, you would get 1.225 meters per second squared. So as stated in the problem, our radius is given. So it's 1.50 meters. So the formula for the angular acceleration is acceleration over the radius. So using this formula, let's just plug in the values. 1.225 meters per second squared divided by 1.50 meters. And then you would get 0.82 radians per second squared. So this is the angular acceleration of the disk in radians per second squared. It's easy. It's pretty easy if you know the formulas. So take note of the formulas that we've used so far in the previous problems up until now. Okay, so for the last problem, problem 3C, still with the same 19th century mechanical elevator. So through what angle in radians and degrees as the disk turned when it has raised the elevator to 3.30 meters between floors? So it's asking the angle in radians and degrees as the disk rotates or has turned, so that the elevator can rise up to 3.30 meters between or from the floors. So we list that down because as we stated in the previous problem, or in the previous slide, that the arc length is equals to the displacement of the cable. So the disk turned when it has raised the elevator to 3.30 meters. So the displacement is equals to the arc length also, or the arc length displacement. So we list that down as the arc length. So S is equals to 3.30 meters. And as stated also in our previous slide, the radius is equals to 1.50 meters from the 3.00 meter diameter. So we divided that by 2 and we would get the 1.50 meter radius. So theta is equals to S divided by R, notice that we will use the same formula that we also have used in problem 1, which is theta is equals to arc length over or divided by radius of the circle. So, using this formula again to find the um, the radian units of the displacement of the angle, we would get so 3.30 meters divided by 1.50 meters, we would get 2.2 radians. This is the angle that you had that resulted to when the disk rotated. So so it's in radians, but the problem is also asking for it in degrees. So using the previous concept of a problem, we would multiply this. So 2.2 times you can actually use these values. So if you try to compute in your calculator that 180 divided by pi, it would equate to 57.3 degrees. So you can actually use this value also to convert radians into degrees. So yeah, so in this case, I'm also showing this method to you guys. So you would have options to solve or to convert radians to degree units. So if you forgot the formula, you can use this value, or if you forgot that 1 radians is equals to 57.3 degrees, you can also use the 180 divided by pi to convert radians into degree units. So using this, so 2.2 radians times 57.3 degrees would equate to 126.06 degrees. So this is the degree units from radians to degrees. Okay, so we're done with the problem. Thank you guys for watching. I hope that you have learned something from this video. So it's my first time teaching, so please take it easy on me. Feedbacks are welcome. Construction criticisms are welcome. So thank you so much for watching this video. Please like and subscribe. Thank you.